Great. Okay, thank you very much. So I'd like to thank my fellow organizers for asking me to join them in organizing this meeting and for asking me to speak. I note that at many conferences, the last speaking slot is traditionally reserved for the crackpot session, and so I again want to thank people for giving me this coveted spot, so that you will know exactly what to expect from this talk. I should mention that unlike Luis, I'm not planning to summarize anything. However, I hope there will be at least some connections in this talk between various things done in this conference. Now, when he started off the discussion section, Doug did something very important, which was that he had each of the speakers give the punchline for their talk, so a sort of quick summary. And in fact, many, many years ago, when I was a graduate student, Bob Wald told me that, well, when you give talks, you should start out with your punchline because that's the only part of your talk that anyone will remember. Okay, so my punchline is the following. Tetrad methods in numerical relativity have turned out to be very useful for the study of space-time singularities, and I'm a bit surprised that they are not more widely in use in numerical relativity, and maybe they ought to be, and we might want to move in that direction. Now, a few of you will think that in giving a punchline like that, I am really pressing my luck. And the reason is that a few of you will remember that about 16 or 17 years ago, I went around giving talks saying, harmonic coordinates have proven really useful in numerical relativity in the study of space-time singularities, and maybe they should be more widely used in numerical relativity, and we should look into this. For those of you who are sort of worried that I'm really pushing it on this, let me assure you that I don't think the Tetrad methods will be anywhere near as useful in numerical relativity as harmonic coordinates. However, I think they can be of use, and that we ought to look into it. Okay, so here's the outline of the talk. So I'm going to start by just reminding you of the standard way of setting up calculations in general relativity using coordinate component methods. And then in contrast to that, I'm going to explain how things go in tetrads. Then, since, as I said, these things are mostly used in the numerical side of relativity for space-time singularities, I'm going to give you a sort of capsule summary of space-time singularities, and then how tetrads are used to study them. And then I'll end by saying, sort of what we might do more generally to use tetrads in numerical relativity. I will end with some open questions. I have open in quotes because what it really means is questions I don't know the answer to. Now, it may be I don't know the answer to them because they really are open in the sense that, the usual sense that no one knows the answer, but it also may be that, well, I don't know the answer because I am ignorant, and someone in the audience will pop up and say, oh, the answer to that question is such and such. So if so, this will have been a really useful conference for me. Okay, so let's get started. So relativity is different from many other areas of physics. In most areas of physics, we have these wonderful inertial frames and corresponding time and space Cartesian coordinates that have direct physical meaning. The usual Cartesian time coordinate t corresponds to time elapsed on the clocks of inertial observers. The usual Cartesian coordinates x, y, and z correspond to lengths measured by the rulers of those observers, or lengths inferred using radar-type methods. Okay, general relativity has none of that. There are, sort of free-fall observers in their local inertial frames, but there's no coordinate system that we should prefer over any other coordinate system. And so we've sort of adopted the attitude that, look, all coordinate systems are on an equal footing. They have no direct physical meaning. Adopt whatever coordinate system is most convenient for the problem at hand and do your calculations. Okay, so what are the ingredients of general relativity? So I want to say this first in a sort of geometric way, and then, give you the usual coordinate component stuff, and then the corresponding tetrad stuff. Okay, so we have a metric, right, which gives the elapsed proper time on clocks of observers. And once we know what the metric is, there exists a unique covariant derivative, a unique connection, for which covariant derivative of metric is 0. Unlike coordinate component derivatives, covariant derivatives don't commute. And so there is this tensor, the Riemann tensor, such that if I take two covariant derivatives in opposite orders and subtract them, that what I get is the Riemann tensor acting on the corresponding quantity. And the Riemann tensor is very important to us because if I contract two of its indices to get the Ricci tensor, then set that equal to 0, that is the vacuum Einstein field equations. And I can set it equal to other stuff corresponding to various types of matter fields. Okay, so that's the capsule summary. We've got a metric. There's a corresponding connection and a corresponding Riemann tensor, and from that we have the Einstein field equations. However, the fact that there is this geometry doesn't particularly help you to write down anything. And in particular, remember, both for the mathematics of partial differential equations and for numerical relativity, we need to be able to write down Einstein's equations as a bunch of partial differential equations. And even more than that, as emphasized by Oscar and Fernando and David, they can't just be any old partial differential equations. They better be ones for which there's a well-posed Cauchy problem. Okay, so what do we do to actually calculate anything? So the standard thing is to say, well, we've got a coordinate system. And once we have a coordinate system, we have the coordinate components of the metric, right? So it's a sort of 4x4 symmetric matrix of coordinate components. And we can write down what the covariant derivative does as well. It's just the ordinary coordinate derivative plus some correction given by the Christoffel symbol. And we actually have a formula for the Christoffel symbol in terms of the ordinary derivatives of the metric. Furthermore, given that this is the formula for the Christoffel symbol and this is the formula for covariant derivative, you can easily convince yourself that if you plug these formulas into this one, that you could obtain a formula for the Riemann tensor that basically just involves derivatives of Christoffel symbols and squares of Christoffel symbols, and then and if you think of the Christoffel symbol by this formula, then you're talking about things that involve second derivatives of metrics and squares of first derivatives of the metric. And so, that then is Einstein's equation as a bunch of partial differential equations. Okay, so this is, in fact, the standard way of thinking about things. And many people during this conference have basically written it down and said, OK, this is what we're doing. However, there's another route to writing down Einstein's equation as a bunch of differential equations. And it's a similar route, but it is in a way, sort of more friendly to people who sort of like to think of things in terms of forms and exterior derivatives, although, as I'll explain in a minute, not necessarily quite as friendly as one might like. Okay, so the idea is that instead of giving the metric, what you do is you give a tetrad, which is just a fancy name for a set of 4 vectors that are going to be orthonormal. So there's going to be one time-like vector and 3 space-like vectors, all of them of unit length, and each of them orthogonal to each other. And when I say give them, right, I mean that sort of sounds vague and abstract, but I mean in exactly the sense as you give a metric by giving its coordinate components. In other words, I have 4 vector fields, I have a coordinate system, and what I'm supposed to do is to give you the coordinate components of each of those vectors, right? So for the metric, I had to give you 10 numbers. For the tetrad, I have to give you 16 numbers, right? Each of the 4 components of each of the 4 vectors. Now, there aren't any preferred tetrads, just as there are no preferred coordinate systems. But at least a tetrad has a slightly more direct geometric meaning than a coordinate system, right? I mean, the time-like tetrad represents a possible observer. Parameter along that is that observer's proper time. the three spatial vectors of the triads can be thought of as the rulers in the Cartesian directions x, y, and z, corresponding to the rulers that that observer might carry along with him. So, so in a way, right, you can think of tetrads, certainly not as being a preferred structure, but at least as being a more geometrical structure than just some floppy set of coordinates. Now, once I've determined the tetrad, that determines the metric. And the easy way to see this is that we remember that given a basis, that immediately determines the dual basis of one forms. And so now if I have the one forms, E0, E1, E2, E3, then you can easily convince yourself that the way to make the vectors orthonormal is that the metric is just minus E0, E0, plus E1, E1, plus E2, E2, plus E3, E3. So giving the tetrad definitely determines the metric. It doesn't go the other way around. Given a metric, there's lots and lots of tetrads. In fact, you can easily convince yourself that the reason I need sort of 16 of these numbers is that the remaining 6 degrees of freedom past determining the metric are just the possible Lorentz transformations among different tetrads. Sure. So at this point, this A, well, you could think of this as the sort of coordinate components. And so little a is the t component, x component, y component, and z component. And capital A is which vector I'm dealing with. So when A is 0, that's the time-like vector. When A is 1, that's the first space-like vector. When A is 2, it's the second space-like vector. And when A is 3, it's the third one. Yes, yes, exactly. You're right. Well, I mean, you can think of this upper index little a as being an abstract index, and some of you will like to do that, but you can also be concrete and say, look, I have a coordinate system. Little a says the coordinate component, big A says which of the 4 vectors I'm dealing with, and so there are 16 numbers, and that's probably an easier way to do it. Say again? Is what SO4? Oh, I see. Well, I mean, I think you can use any ordering you want. I mean, the usual one is that the volume form will be sort of 0, 1, 2, 3, 4. But even then, it's not going to be 04 because time is different from space. So it'll be 01. Oh yeah, 3, 1. Right. Okay, so now let's talk about tetrads as a way of computing things. So the basic idea is the following. Remember that in computing covariant derivatives in the coordinate basis way of doing stuff, what you're supposed to do is you're supposed to take coordinate derivatives of metric coordinate components, and that allows you to compute the Christoffel symbols. And once you know the Christoffel symbols, then you can take the covariant derivative of anything. Here the idea is that any vector is equal to, a linear combination of the basis vectors. And so if I know how to take a covariant derivative of the vectors in the tetrad, I know how to take the covariant derivative of anything. So basically, what I have to do is I have to compute the covariant derivative of each of the tetrad components. Well, that's going to be something that, lives in the tensor space of type 02, and so it's determined by what I get when I contract it with any of the other tetrad bases. So now I really am just about computing numbers. So the idea is there are these quantities, omega sub a, b, c, where again, a, b, and c are numbers that go from 0 to 3. And I'm supposed to compute something for any of them. And And the idea is to compute the number omega ABC, called the Ricci rotation coefficient. What I'm supposed to do is I'm supposed to take the covariant derivative of vector C, and then I'm supposed to contract with vectors A and B. So the idea is if I can compute these numbers, then I know how to take the covariant derivative of anything. Just as, you know, in the old way, if I compute the Christoffel symbols, I know how to take the covariant derivative of anything. OK, now, so you might think that this is a lot of numbers to compute, but not quite as many as you might think. The fact that these vectors are unit means that this quantity is actually antisymmetric under B and C. Right? So there's really only 6 of these in the BC indices and then 4 in A, so only 24 numbers to compute, which is not as bad as Christoffel symbols, because Christoffel symbols are symmetric in their bottom 2 indices, and so there are really 40 of those to compute. OK, so how do we compute these things? So remember that for the Christoffel symbols, we knew how to compute them because we had a formula that just involved ordinary derivatives with respect to the coordinates. So there's something similar here. It turns out that you can determine these Ricci rotation coefficients using only commutators. And remember, commutators you can compute with any derivative operator, including the coordinate derivative operator. So the idea is there are these other numbers, also antisymmetric under B and C, which is basically just take the commutator between vector B and vector C and contract with vector A. And once you've computed all these, there's a very simple formula, which for some reason the textbooks don't bother to write down, for how you get the Ricci rotation coefficients from these. So what you want to think of is this is basically the same sort of stuff that we did with coordinate components and Christoffel symbols. The idea is once someone hands you a tetrad, what you want to do is you want to calculate all possible commutators and then contract them in this way. And now you've got all these numbers. You use these numbers to get the Ricci rotation coefficients. And once you have those, you can take the covariant derivative of anything. Now, for reasons that I'll get into later, it's this formalism which, in terms of commutators and vectors, which generally gets used in the numerical applications. However, I want to mention that there's an analogous set of formulas which you may, in fact, be more familiar with, having to do with, instead of vectors and commutators, with one-forms and exterior derivatives. So remember that, you know, instead of giving a basis of vectors, I could instead give a basis of one-forms. And having a basis of one-forms, I would then get from that the dual basis of vectors. So it's easy to go back and forth between, you know, this is my set of tetrad vectors, and this is my set of 4 orthonormal one-forms. Well, once I have one-forms, I can just take their exterior derivatives, just using ordinary coordinate methods. And then there's a formula sort of analogous to this for how you get the Ricci rotation coefficients from those exterior derivatives. OK, so that's basically the introduction to tetrads. Let me just sort of summarize a few things with this. So just as you could easily convince yourself from the formula for the Ricci tensor that in coordinates you could write this in terms of Christoffel symbols, their derivatives, and their squares, similarly, you can convince yourself just from that abstract formula that there must be a formula for the Ricci tensor involving these Ricci rotation coefficients, their squares, and their derivatives along the tetrad direction. So in fact, the way that you get a bunch of differential equations corresponding to the Einstein equation is that you regard the definition of the commutators as basically being a formula that allows you to evolve the tetrad, and you look at the Einstein field equation as a way that allows you to evolve omega. So you can easily now see that, well, we get a bunch of first-order partial differential equations for the tetrad and the Ricci rotation coefficients, and then as long as this has a well-posed initial value formulation, we're up and running. Okay, so at first sight, this sounds like it's more work, right? Because we managed to get away with only 10 metric components, whereas we have to give 16 tetrad components. But in fact, the fact that we only have to compute 24 Ricci rotation coefficients versus 40 Christoffel symbols means that this will actually, save you work in the long run. Both. So in the tetrad language, components are no longer coordinate basis components. They are tetrad components. So yeah, so that's exactly what I mean. Okay, so now, having given you, David insists on calling this my tetrad boot camp. So now, having given you the introductory, couple of page, this is what tetrads are, I'm going to do the same for space-time singularities. Okay, so we know that stars are held in equilibrium by the opposing forces of their pressure, which try to push them outwards, and their self-gravity, which tries to pull them inwards. And we sort of have an idea for why there should actually be an equilibrium, right? We know that when you take matter and you compress it, that the sort of smaller you make it, the harder it resists, right? In other words, that pressure is an increasing function of density, and so you figure, okay, well, eventually, the pressure must get big enough to resist gravity. However, right, gravity is a 1 over r squared force, and so what that means is that as the star gets smaller, its gravity gets stronger too, and so there's no particular obvious reason why there should be an equilibrium, right? Maybe as the star gets smaller and smaller, pressure gets bigger and bigger, but gravity gets bigger and bigger even faster, in such a way that there's never an equilibrium and gravity always wins. So that this was possible for stars was first realized by Chandrasekhar, and he used it to calculate a maximum possible size for a white mass for a white dwarf star. Now, general relativity adds sort of an extra wrinkle to this, because once the object gets sufficiently small that it's inside its own Schwarzschild radius, then there's basically nothing that can resist further collapse. And so we expect the entire star to just keep on collapsing until it's reached a region of infinite curvature, or at least a region where curvature is sufficiently large that we don't trust classical general relativity anymore. Okay, so this expectation is bolstered by the singularity theorem of Penrose. So basically, Penrose's singularity theorem says that once you form a trap surface, which, as Pablo mentioned in his talk, is basically a surface where even the outgoing light rays are pulled to converge, then with a few sort of simple assumptions like no closed time-like curves and energy is positive in a certain sense, Penrose proves that the space-time must be singular. However, it's a very funny notion of singular. So Christodoulou and de Fermos like to say that these things should never be called singularity theorems. They should be called incompleteness theorems, because what Penrose actually proves is that at least one geodesic ends, right? And that's it, right? Nothing about density blowing up, nothing about all observers ending. All we know about the singularity, all we get from Penrose is that for some reason some observer or light ray ends, and that's all he tells us. So I mean, this theorem is wonderful because there's very general circumstances, right? I mean, you don't have to assume much. A trap surface, energy is positive, no time machines, and that's all that goes into it. But it's very frustrating because it gives us very little information about the nature of singularities. So what are singularities actually like? Well, Penrose doesn't tell us. Okay, so what do we expect? Well, we expect especially, you know, given the hindsight of many years of treatment of nonlinear partial differential equations. Well, okay, this is going to be a set of hyperbolic nonlinear partial differential equations. Such equations often have blow-up. We expect that there ought to be some kind of blow-up. And furthermore, we remember that for lots of PDEs, when there is blow-up, some terms dominate over others, and the blow-up is actually simpler than the general solution. So that's sort of what we would expect. Okay, so the trick, though, is to try to figure out, you know, which terms are more important, you know, which are the terms that dominate in the approach to the blow-up. So there's an old conjecture, about as old as the Penrose theorem, due to Belinsky, Kalatnikov, and Lifshitz, that near a singularity, the terms that dominate are the time derivatives, and compared to them, the space derivatives are negligible. So if this is true, what this means is that near a singularity, Einstein's equation is, you know, much simpler than it is in general, and we might be able to get a nice handle on how space-time singularities behave. Okay, well, people, you know, sort of debated back and forth for a while about, you know, whether this was any kind of reasonable assumption. I mean, what what Belinsky, Kalatnikov, and Lifshitz basically showed is that, well, at least this assumption isn't massively inconsistent with the Einstein field equations, but they didn't show that things actually happen this way. And so in the 90s, Beverly Berger and Vince Moncrief started a research program to do numerical simulations of space-time singularities and see what happened, and in particular to see whether this conjecture is right. Okay, so now what I want to do is to show you a singular space-time. And this is a very simple singular space-time, but remarkably, you're going to find that this thing has most of the stuff that we need to know about general space-time singularities. Okay, so here it is. So this is the metric. So the time-time component is -1. The space-space components are all powers of t. And if you go ahead and compute the Ricci tensor for this, you find that this is a solution of the vacuum Einstein equations, provided that the sum of these three numbers, p1, p2, and p3, is 1, and the sum of their squares is also 1. Now, given these two conditions, it turns out that one of the p's is negative. And this is perhaps a little bit surprising. So in this way of doing things, the singularity is at t equals 0, sort of like it is in the usual Robertson-Walker metric for cosmology. So you can sort of think of this as being like an anisotropic cosmology. But the fact that two of these things are positive and one of them is negative means that in the approach to the singularity, only two directions are contracting and one direction is expanding. Okay, and that seems like a sort of strange thing to do. However, remember that one singularity that we are familiar with is the Schwarzschild singularity. And in fact, if you look near the Schwarzschild singularity, you will find that it behaves exactly like this, with the particular values p1 is equal to -1/3, and p2 and p3 are equal to 2/3. So what's going on here? What's expanding in Schwarzschild? Well, remember that in Schwarzschild, once you're inside the horizon, space and time switch roles, and so the theta and phi directions are contracting as you go toward the Schwarzschild singularity, but t, which is a space-like direction now inside Schwarzschild, is expanding. So among other things, this describes how the Schwarzschild singularity behaves. It's just a particular special case of one of these. Okay, so that is a simple homogeneous space-time, homogeneous meaning it's the same at every point of space. What about a general homogeneous space-time? Well, it turns out that a general homogeneous space-time looks like a sequence of these Kasner spacetimes punctuated by rapid, but not infinitely rapid, transitions where the p's change from one set of values to another set of values. These the rapid transitions are somewhat confusingly called bounces, and that's the traditional terminology, and I'm going to adopt it here, even though it's a little bit misleading. Okay, so, well, all right, so now we've built up from this, simple Kasner to the general homogeneous, but yeah, go ahead.
When you say turns out, that means that it's like an empirical, numerical finding?
Well, I mean, so it started out that way, but remember, ordinary differential equations are things that you can prove stuff about. So in particular, there's a theorem of Ringstrom that it does behave that way. Yeah. Yeah, I mean, remarkably, it took a lot of work for him to prove that theorem, but it is a theorem. So yeah. Okay, so all right, so but general spacetimes are not homogeneous, and so it sounds like, well, okay, I've told you all the simple stuff, but it's not going to be very much good in analyzing the general case. But remember, if this BKL conjecture is right, then that means that since at each spatial point the spatial derivatives are negligible in the equations of motion compared to the time derivatives, that means that each spatial point has a dynamics that behaves exactly like one of these homogeneous spacetimes. That doesn't mean that space is becoming homogeneous, because the idea is that it's a different homogeneous spacetime at each spatial point. But nonetheless, right, if this is right, that means that space-time singularities actually have fairly simple behavior. Okay, so now I want to get to, well, what should we use to simulate this? So one of the things I want to point out is that because of the coordinate components behaving like all sorts of different power laws, some positive powers and some negative powers, that means the inverse metric also has this different behavior, and in fact the Christoffel symbols are going to be all over the place. Some of them are going to get bigger, some of them are going to get smaller. However, and this is the thing that sort of recommends the Tetrad system in this case, if you calculate the commutators in the Kasner spacetime, you will find that the commutators and the Ricci rotation coefficients all behave the same way. They all behave like 1 over t as you go toward the singularity. So the point is that Kasner and therefore hopefully by extension general singular spacetimes look much simpler in tetrads than they do in coordinates. I mean, they look already fairly simple in coordinates, but in tetrads everything has uniform behavior, and that's going to be important in a minute. But the basic idea is that gives an argument for why, if you want to do a simulation of the approach to a space-time singularity, you might be better off using tetrads than using coordinate components. So the tetrad components themselves don't, but that's also going to be important. But certainly the Ricci rotation coefficients do, and the tetrad components of the Riemann tensor all scale in the same way. And in fact, the different scaling of the tetrad components is also going to be very important for the BKL conjecture, as I'll get to in a minute. Okay, now as Pablo emphasized in his talk, you don't want to have your code hit the singularity, because once it does that, then all bets are off. However, if you want to study space-time singularities, you want to be able to get arbitrarily close to the singularity. And that, by the way, was also one of the nice properties of harmonic coordinates, that harmonic time slicing gets you arbitrarily close to the singularity. But there are other ways to do that, and in particular, if you foliate space-time by surfaces of constant mean curvature, and in essence use the constant mean curvature as your time coordinate, then those slices also get arbitrarily close to the singularity, right? So the singularity is basically the place reached by your foliation in the limit of infinite constant mean curvature. Okay, so the idea then for how to do this simulation is we're going to pick the time coordinate. Well, we're going to foliate by surfaces of constant mean curvature. That's our time coordinate. We're going to pick E0, the time-like member of the tetrad, to be normal to this foliation. The space-like stuff of the tetrad, we'll pick sort of arbitrarily, but then as we evolve, we'll just firmly propagate them. So once you do that, if you write out the commutators, you get the following quantities. And I want to call your attention to a couple of these things. So this h is basically just the average expansion of the slice. Sigma is usually called the shear. It's the thing that tells you that different directions are expanding at different rates. There's no intuitive, way I know of to say what these things in the commutators of the spatial metric are. But again, thinking about tetrads as being, sort of the analog of what we usually do with coordinates, you can think of these as basically being a decomposition of the sort of spatial Christoffel symbols. Okay, so now here's the point about everything scales in more or less the same way. What you want to do is to take the triad vector components, the shear, and these spatial Christoffel symbols, and divide each of them by the average expansion to get a bunch of scale invariant variables. So the idea is that if things blow up at the same rate, then that means that even as you go to the singularity, as everything physical is blowing up, that the stuff on the left-hand side, which is what you're going to actually evolve with the code, that stuff remains finite. So now you can do a numerical simulation of a singularity where, everything is going to hell and your code doesn't even notice. Okay, so that's the idea. So now I want to address the point that was raised earlier about, well, what about the tetrad components? Do they all scale the same way? So it turns out that they don't. And this becomes important because when you write the Einstein field equations, every spatial derivative is multiplied by this rescaled triad vector. So now the BKL conjecture becomes the conjecture that actually the physical spatial triad vectors blow up more slowly than the time one, and that therefore when you do this rescaling, that this rescaled spatial triad vector goes to 0. So now you have a nice simple way of saying, well, this is what we're looking for to see if BKL is right. Furthermore, Kasner, which was already sort of simple enough in coordinates, is even simpler in rescaled tetrad variables. So Kasner is just characterized by the rescaled shear as constant, and the rescaled spatial Christoffel symbols are 0. Right? So that's sort of an easier way to say what Kasner is.
Just to clarify,
Yeah.
So the coordinates from your tetroids are well defined over the singularity, in the neighborhood of the singularity.
Well, I mean, so nothing's well defined at the singularity, but they're well defined arbitrarily close to the singularity.
So it doesn't matter from which direction I approach the singular point.
Well, within general relativity, it's much better to think of the singularity as a space-like surface rather than a single point. I mean, it's true that in other contexts we're used to thinking of singularities as there's a spatial point and things are going bad there. But you're going to find that in this context it's much better to think about, everything is going to hell at a particular time at all points in space. And that bad time at all points of space is the singularity. Other questions? Okay, so now we're also able to say what these sort of transitions from one Kasner to another are. So if we look at homogeneous spacetimes in this language, what we find is that there are periods in which sigma is approximately constant, and this spatial Christoffel symbol quantity n is 0. But we find that in general, at least one component of n grows, and it grows large enough to trigger a transition in sigma, which in turn makes that quantity go back to being small again, and so you get another Kasner era. So it's also very simple to characterize what these so-called bounces are. Finally, since, as Oscar told us, we need a well-posed initial value formulation, it turns out that within this constant mean curvature foliation, you get an elliptic equation for the lapse that maintains the foliation, and then everything else, the evolution equations for the tetrad components and the Ricci rotation coefficients, becomes a set of hyperbolic equations. So that's something you can put on the computer. You basically go ahead and tell it to evolve according to the hyperbolic equations, and then at each time step you solve the elliptic equation for the lapse, and that gets you to the next time slice. Okay, so what do we find? So first of all, I'm going to sort of tell you in words, and then I'll show you a few graphs and movies. So sure enough, we find that the spatial derivatives do become negligible. Again, not because they're small, but because in the field equations they're multiplied by small quantities. At each spatial point, you get dynamics that looks like the dynamics of a homogeneous space. So that's what happens in the vacuum case. In the scalar field case, things are very similar. You still get this sequence of Kasner bounces, except in contrast to the vacuum case, there's a last bounce, and then you go all the way to the singularity with the Kasner exponents of that last value. And this is in accordance with the Fuchsian results of Rendell and Anderson and the theorem on stability of scalar field Kasner due to Rudniansky and Speck. And finally, if in addition to a scalar field you give it a very extreme kind of negative potential, then you can go to the singularity in such a way that everything smooths out and you just approach Robertson-Walker in accordance with the bouncing cosmology scenarios of Steinhardt. Okay, so now I'm going to show you a few graphs in a couple of movies. So this is the components of the rescaled shear sigma on our way to the singularity. And again, it's kind of funny because here I'm telling you that, well, this is a singularity, but you look at this graph and nothing is blowing up. So the thing to remember is that, so the coordinate here is a sort of logarithmic coordinate. So in other words, the mean curvature is basically e to the minus t, which means that the Kretschmann scalar is something of order 1 times e to the minus 4t. So now I go to these large negative values of t, and I tell you that the Kretschmann scalar is something of order 1 times e to the minus 4t, and you can easily see that in this sort of wimpy-looking numerical simulation, I have an absolutely enormous Kretschmann scalar. In fact, this little simulation is enough to take you from, say, the kilometer scale of a collapsing star to the Planck scale, where you no longer trust classical GR anyway. So even though it looks like not much is going on, you're actually getting to enormous curvatures. Yeah. In this one, none. This is a fully 3D simulation. However, the output of this simulation, I'm sticking at a particular spatial point and just asking, okay, at that point, how do things behave? And sure enough, what we get are these, sort of Kasner transitions where things are approximately constant and then they change rapidly. And in the same simulation, this is what happens to the corresponding components of n, the rescaled spatial Christoffel symbol, right? They're 0 most of the time, and then they get big, in a short time, trigger a transition, and then go back again to 0. So even though there's no symmetry involved whatsoever, nonetheless, if you, hang out at a spatial point, you find that it's behaving exactly as though it were part of a homogeneous spacetime. Okay, so now here's the same thing. I've sort of written it as minus t in this case, so now you can sort of follow from left to right in the progress to the singularity. The other one was from an earlier paper when we didn't realize how confusing that would be, and now we switched over. So with a scalar field, it's the same sort of thing, except there's a last bounce, and then you just go towards the singularity in exactly this sort of Kasner way, just as Rendell and Anderson and Radyansky and Speck tell us you ought to. And here again, these transitions are triggered by these spatial Christoffel symbols n, but after a while, none of them grow anymore, and you don't get any more transitions. Okay, so now let me show you some movies. So that's what things look like hanging out at a particular point. If instead we sort of look in a plane, then we get something. So this is sigma. You start at one thing, and then you go through a transition, not all the same place, and then you bounce to another one. And then finally, let me show you another movie corresponding to this Steinhardt scenario where you add a scalar field and a negative exponential potential. And what I'm going to show here, let's see, let me hang on a second. Let me pause this and go back to the beginning. Let's see. Well, I'll play it once and then play it again. So basically the idea is when you start out, you have some scalar field, but you also have an enormous amount of energy in the shear and an enormous amount of energy, just in a whole bunch of inhomogeneities. And what you find is that when you evolve, things eventually put all their energy into the scalar field, and everything smooths out, and you get to Robertson-Walker. So here, let's see. Hang on a second. Yeah, let me just start that one over. Yeah. Yeah. So you basically have a whole bunch of inhomogeneities, all sorts of nasty stuff. And then you evolve, and eventually everything smooths out. All the energy is in the scalar field, and so in contrast to what usually happens in GR with either no matter or with most of the kinds of matter we're used to, this is a case in which even in a gravitational collapse problem, you can actually prepare something which looks just like the expanding universe in reverse. Of course, to make the rest of the scenario work, you actually now have to make that bounce from a contracting universe into an expanding universe, and that's a little bit harder because you have to violate the null energy condition, but that's an entire other story. Okay, so that's the stuff about singularities. Now let me go back and to this, sort of what else might we do with tetrads? So in particular, what I've given you is a well-posed initial value formulation for these scale invariant tetrad variables. I mean, that's the sort of thing that you'd want to do if you were studying singularities. But if you wanted to use, tetrads to study critical collapse or to collide black holes or to study neutron stars, you would want a plain old, ordinary tetrad system. So you want a non-rescaled tetrad system that also has a well-posed initial value formulation. Now, such systems have been devised by Helmut Friedrich. However, Helmut, like Doug, really likes the Weyl tensor and the Einstein-Bianchi system. And so all of Helmut's systems involve adding the Weyl tensor as one of the variables and adding the Bianchi identities as equations to evolve those. However, right, this isn't quite as simple as what Doug showed you, because as David pointed out yesterday, if you're doing this in full general relativity as opposed to linearized gravity, it's not okay to just evolve the Weyl tensor. You also have to evolve the tetrad and the Ricci rotation coefficients. But nonetheless, there are these nice systems due to Helmut Friedrich where you have this set of evolution equations, and the Ricci rotation coefficients tell you how to evolve the tetrad. The Weyl tensor tells you how to evolve the Ricci rotation coefficients, and the Bianchi identities tell you how to evolve the Weyl tensor. So it's a very nice, elegant-looking system. And then the question is, is this something that we should try numerically? And I'll get to that a little bit in the next one. However, those aren't, I mean, you're not forced to add the Weyl tensor. I mean, sort of Helmut likes to do that, but it's at least possible to, make some, non-rescaled tetrad system where, everything closes and you get, a nice hyperbolic system with just using the tetrad and the Ricci rotation coefficients, and you're not forced to add the Weyl tensor as the variables. Okay, so one of the things that we could do is to try this more generally and see whether it's any good for some of the things that we usually do using numerical relativity. Okay, so now I want to switch to open questions, and again, these are open in the sense of I don't know the answer to them, but if you happen to know the answer, please let me know. Okay, so the first one I've already alluded to. Well, I think I've alluded to all of them, I guess. So the first one is, other than the singularity stuff where these things have proven very useful, are there other areas in numerical relativity where, we should try this out and where we might think things are going to be helped by using tetrads rather than coordinates? Okay, so if we do that, then one of the first questions is, should we use the Weyl tensor as one of the variables and correspondingly use the Bianchi identities as evolution equations? The pro, right, the why should we do this, I mean, aside from sort of, oh, this is an elegant system and we want to try it out, is that in many cases, the thing that we want to calculate actually is the Weyl tensor. So as Deirdre emphasized in her talk, when we give waveforms for LIGO, what we're really calculating is psi4, namely the most slowly falling off component of the Weyl tensor. So if what we want when we collide black holes is to calculate the Weyl tensor, maybe we ought to just go ahead and make the Weyl tensor one of our variables. So there are arguments in favor that, well, okay, it's an elegant system, and some of the quantities that we're adding when we add the Weyl tensor are the things that we're most directly interested in. However, there's an enormous argument against that was provided many years ago, not in the context of this system, but in the context of other ones by Lee Lindblom, and that has to do with the fact that any time you add more variables, you're adding more constraints. And any time you add more constraints, you have the possibility that blowing up constraint violation will just kill your code. Right? So we learned that lesson from Lee so well that now we're all sort of gun shy about I want as few variables as possible because any constraint can kill me. On the other hand, we've also gotten pretty good at constraint damping, and so one of the sort of a sort of subsidiary open question of this open question is can we think of an effective constraint damping method that will work even if we add the Weyl tensor and the Bianchi identities. Okay, and then finally, even though these systems are typically written down in terms of commutators rather than exterior derivatives, right? So this is written down in terms of vectors and commutators. There is, in the tetrad formalism, an equivalent way of writing things down in terms of one-forms and exterior derivatives, and that might sit better with some of the methods we've been hearing about in this conference. However, in order to make that work for numerical relativity, one needs not just a set of equations in terms of one-forms and exterior derivatives, but a well-posed initial value formulation in that form. And I'm not aware of one. So one open question is there one out there that I just don't know about, in which case, you should tell me. And if there isn't one out there, can one find one, right? I mean, is there a way of writing Einstein's equation, mostly in terms of one forms and exterior derivatives? If so, many of the sort of exterior calculus techniques that we've learned about in this conference might have a direct application in numerical relativity. Okay, so that's it. That's all I had to say. Yeah.
So just a comment, a couple of my postdocs at Caltech years ago actually coded up one of these vile tetrad things and published a couple of papers. Louisa Buckman and I think Olivier Sarbach was part of that.
Oh, great.
So
Oh, wonderful.
A paper or two. I don't remember exactly what test they ran, but anyway, it faded away and didn't get used very much. But it has been done.
Okay. Is this something easy for me to find by a search? And if not, maybe you could send me the reference?
Well, I would have to search for it too. But
Okay. All right. I'll find it.
Get together and try.
Yeah.
I think Bardeen was on part of it. I think there's more than one paper, but Bardeen was on one of them.
Yeah. Okay. All right. Great. Thank you. Yeah, Oscar?
Some equations for the Tetrad and for the forms which are ordinary differential equations, and then just by identity with some more constraints.
So are these helmet systems with the Weyl tensor or non-helmet systems without the Weyl tensor?
With the Weyl tensor.
Okay. Yeah. Well, right. So those I know about. Yeah. I mean, I know about the ones with the Weyl tensor.
The part for the Tetrad and the omegas are not the same. Different equations. But you use the Weyl identity with some more constraints.
Okay. Right. Okay. Okay. Good. Good. So where do I find these?
I've never found it, but there must be several people.
Okay. Well. Okay. Great. Yeah, I'd definitely like to see that. Yeah. I mean, I've devised. I've never seen it either, but sort of without the Weyl tensor. And I mean, I've devised a system using harmonic slicing where you don't use the Weyl tensor, just the Ricci rotation coefficients and the tetrad, and things close and they certainly look like they're hyperbolic. But I haven't seen it in the literature anywhere. But you're saying you sort of did this but didn't publish it or something, or you're sure somebody else has published it but you haven't seen it? Yeah, that's sort of what I thought too, but I mean, how come we haven't seen it? Okay, well, we should talk about this some more. Yeah. Yeah.
I have a question about the amount of work you have to do. I can see that with the Ricci rotation coefficients, you clearly have less stuff in memory.
Mm-hmm.
When you compute them, you have to compute commutators, not partial derivatives. So in the end, I think you still need to compute 4 times 16 partial derivatives. So it seems like it is actually more work than computing the double symbols. Or do you have a trick to avoid having to compute some of the partial derivatives of the components of the tetrad?
Let's see.
You see what I mean? There's a distinction between computing partials and computing commutators. In commutators, you're going to need partials of both.
Yeah, I see what you mean. Yeah, but I see. Okay. Right. Okay. So let me sort of let me kind of backtrack on that a little bit. So it's true that if from the sort of Mathematica point of view, that if someone handed you a tetrad, Mathematica might have to do lots of computations to compute its Ricci rotation coefficients. But when you turn this into a set of evolution equations, even though in principle the Ricci rotation coefficients come from all these commutators which you computed with partial derivatives, the actual equations that you have are basically time derivative of tetrad component equals spatial derivative of tetrad component plus Ricci rotation coefficient. Time derivative of Ricci rotation coefficient equals spatial derivative of Ricci rotation coefficient plus Weyl. So the point is that in an evolution code, you're not actually calculating any commutators. You're just evolving stuff. And now, if you have sort of a first order code in coordinates, right? Then in principle, the things that you're evolving are 10 metric components and 40 Christoffel symbols. Whereas if you have a first order code in tetrads, then what you're evolving are 16 tetrad components and 24 Ricci rotation coefficients. So I still claim it's less memory and less computation.
Your final question is, you're saying that you can write down the full Einstein equation in the Tetrad formulation without using differential and using exterior derivatives. So it's not clear that you can formulate that as a hyperbolic system?
Right, exactly. Yeah. Well, and in fact, you sort of know that already, right? I mean, this is what people talk about when they talk about the Einstein-Cartan formulation, right? I mean, that's basically okay, we have this sort of elegant way of writing Riemann in terms of exterior derivative of these connection 1 forms and the connection 1 forms in terms of exterior derivatives of the yeah. So I mean that part is sort of known. What's at least not known to me, but maybe somebody knows it, is whether there's a way of parlaying that into a well-posed initial value formulation. The only sort of well-posed initial value formulations I've ever seen involving tetrads are ones that phrase everything in terms of commutators and derivatives along the vector field. So, I mean, either through a literature search or through, just trying to do this, it would be nice to find out whether there is a way to do a well-posed initial value formulation where you use the other version of the tetrad system, where instead of writing everything in terms of vectors and commutators, you write it in terms of 1 forms and exterior derivatives.
And that formulation is the full gauge freedom, so you have the gauge is one of the tools to try to formulate this hyperbolic.
Yes, yeah, exactly. Exactly. So for example, in the sort of vector version of things, one sort of choice of gauge that seems to work quite nicely is to use harmonic slicing and zero shift, and in that way, sort of everything closes. But there are sort of other gauges as well. So in the sort of vectors and commutators language, this has all been worked out by Helmut Friedrich. I don't know. I mean, I don't know whether there's a way to work it out in the 1 form and exterior derivative language. I mean, maybe Helmut would know the answer to that. I mean, maybe there's a simple way and he just didn't bother to do it because he's already got one he's happy with, or maybe there's some obstruction to doing it, or maybe somebody did it 20 years ago and I just don't know where to find it.
I know he's interested in these tetrad things, and he likes doing everything in terms of differential forms.
Okay. Yeah. Well, I mean, it is well known how to write down, the Ricci tensor in terms of forms and exterior derivatives. But the point is that you need a well-posed initial value formulation, and I haven't. The only well-posed initial value formulations for tetrads that I've ever seen have been phrased in the language of commutators and vector fields.
So let me give you my current concern about this.
Okay.
I agree that
Good.
Historically I was probably worried about constraints, but I agree with you, constraint damping is now a powerful tool that can probably overcome that. But the thing I'm worried about is, so in addition to having gauge conditions that tell you how to evolve the coordinates in a nice way to keep things from going crazy, you're now going to be responsible for developing a nice way of developing the evolution of this tetrad. So you've got this extra point array degree of freedom that has to somehow be specified. And so maybe you can do that in a nice way. You could there are several different these conditions. I think there's a Nestor gauge and there's a Estabrook gauge or something like that that makes the system hyperbolic. But are those really the things that are going to allow physics to come out in a nice way and not go singular when interesting things start happening?
Yeah. Okay. So let me right. So I think I can lay that one at rest at least. So I'm gonna give you my philosophy on this, which you're probably going to think is much too extreme. But I want to start with an analogy, right? So remember that, I mean, once you have a foliation, which you know, it determines what the lapse is, you also get to pick the shift. And you know, historically, people sort of worried about, oh, well, you know, maybe we should make the shift do this, maybe we should make the shift do that. My attitude is, you know, in most cases, the shift is a complete annoyance, and since I'm allowed to set it equal to 0, why don't I just do that and make my life easier? Now, there's something analogous with the spatial triad, right? I mean, so the time thing is fixed, right? I mean, in these initial value formulations, the time component of the tetrad is the normal vector to the foliation. But as you say, there's lots of freedom for picking the triad. So the analog of the shift is, well, the analog of 0 shift is you Fermi propagate the triad. And so the idea is you can choose how the triad differs from Fermi propagation. That's an extra degree of freedom, which is sort of the analog of the shift. And some people do say, oh, let's choose it, you know, to make this nice or that nice. And my attitude is, let's make our life easier by making it 0. So my prescription is, you know, unless you give me a damn good reason, I'm going to choose 0 shift. And for the tetrads, the analog of this is, unless you give me a damn good reason, I'm going to Fermi propagate the triad.
I think nobody has done black hole mergers with 0 shift. So I agree with
Okay.
you. That would be a nice thing to do. It makes the equation simpler, but in practice, it's
You could never break signals with 0 shift.
right.
Okay.
And I worry that there are similar bizarre things about tetrads that will also show up in extreme situations. I don't know them. I'm just telling you what my current worry is, so you can embarrass me in some future comment like, the old days, Lindblom said this.
Well, no. I mean, so my response would be fine. You know, I'll write a code that has 0 shift, and then when I get in trouble, I'll say, oh my God, you know, Lee told me I was going to get in trouble. Now I need to try something more sophisticated. Yeah. So that's the idea. Thank you. Yeah. So just to clarify Luis's comment, over many years, you know, I would ask Matt Choptuik for advice on numerical relativity, and in particular, I would, you know, I'd go with some idea for, you know, hey, I think I can write a code that does this, and you know, his advice to me would invariably be the same. He would just look at me and say, that's an interesting idea. Why don't you code it up and see if it works? And so after a while, I began, you know, I got sophisticated enough I could give myself that advice. But it's good to have Luis remind me too. Yeah, so I think we've probably kept people enough. So thank you very much.